So, um, so I'm a member of the data science group here at Argonne. My background is in high energy physics, doing LHC experiments, running high energy physics simulations at scale on DOE machines. And today I'll talk a little bit about using containerized software, specifically at ALCF. So let's get started. So just quickly, the data science group at Argonne has quite a few people involved, and you can always reach us via datascience@alcf.anl.gov. There are people with various backgrounds, material science, cosmology, high energy physics, computer science, mathematics, energy sciences, biology, genetics. So there's a wide range of expertise in the group. And, if you have specific questions about how to use the ALCF resources, how to do your science at scale, you can always either email support, of course, but if you have data science related questions with workflows or machine learning, feel free to always reach out via the data science email list, and someone will get back to you. So just quickly, I'm sure a lot of people are familiar with virtual machines, and containers are the latest craze, and I just wanted to highlight the difference between virtual machines and containers. Virtual machines not only have all the software included that you need to run your applications, but they also emulate hardware, so all the way down to network interfaces and serial interfaces and so on and so forth. Whereas containers rely on just on the local system's kernel and the local system. They directly access the system's hardware through that kernel. So the only thing that sits inside of your container are the binary libraries, the applications that you build, but you're using the local system's kernel. So it's a little bit closer to the bare metal, including in performance comparisons that I've seen. You get a little bit better performance from containers than virtual machines as well. So containers have recently gained popularity, especially on cloud platforms. These include things like Docker, Charlie Cloud, Singularity, Shifter, Rocket. At the ALCF, we chose to support Singularity instead of Docker, Docker being one of the most popular ones, obviously, but there are security issues where users would be in a situation where they could, in principle, mount anywhere on our file system as root and get escalated privileges, so we couldn't have that running on our machines. So we use Singularity, which is specifically designed for HPC environments and handles these kinds of, or corrects for these kinds of security issues. And I place a link here to some of the Singularity documentation, the Singularity Hub website, which I'll talk a little bit about, and also our user guide for Singularity. And so we have Singularity installed on our local Theta and Cooley resources. Theta is our 10 petaflop Knights Landing machine, and Cooley is our visualization cluster, which is 126 nodes with NVIDIA Teslas installed. So I'll go straight into building containers. So if you're on a Theta login node, Singularity is already part of your path. You don't have to load anything. And if you have a container on Docker or Singularity Hub that you want to use on the system, you can immediately download it with the Singularity build command. Now, if you don't have a container ready that that already exists on Docker or Singularity Hub, you can always build those. And unfortunately, on the login or for Singularity, you require sudo rights to build containers. If you're going to be running either a recipe to build a container or you're going to be editing the contents of the container, you need sudo rights. And of course, we're not going to give you sudo rights on the login nodes. So for custom images, these have to be built elsewhere. So either on your laptop, your own cluster, or you can use Singularity Hub. And so I'll go through how you can do this on Singularity Hub, but you could always, you can also run these on your local machine. For instance, I have a MacBook, I have Singularity installed, and I do a lot of my quick turnaround testing there, and then I upload my recipes to Singularity Hub so that they get rebuilt automatically whenever I make small changes. But the initial development I would do on my local machine for ease of use and speed turnaround. So to use Singularity Hub, obviously you'll need an account, and typically you'll want to install Singularity somewhere you can do this quick turnaround like your laptop, and then you can start building. So let's start with quickly Singularity Hub. You can go to your GitHub, and if you don't have a GitHub account, I highly recommend you getting one. This is how you will use Singularity Hub. You'll first create a GitHub repo which will hold your Singularity recipes. So in this case, you see here, I created just a Singularity images recipe repo, which you can actually find on GitHub, and I'll link to as we go. And then you would go to Singularity Hub and either log in or create an account. In the case of create an account, I would just use your GitHub account and as a method for logging into Singularity Hub, because you're going to link these two things together. And once you do that, you're going to find there's this My Collections page where you can add a collection, and a collection is really just a GitHub repo. So when you click on that GitHub add a collection, you'll have a list of all of your GitHub repos show up, and you can select the Singularity image recipe GitHub that you created. Click submit. I'm going to go quickly through these. The slides are of course meant, they have all the info there, so you can look at them later if you want to go through these steps. And now you'll see your repos in your container collections. And if you click on that container, at the moment this is empty, so you don't have any containers to be built, you don't have any images to be built. So we need to make one. Hopefully the text on these are coming out clear, otherwise I can zoom in on some of these if need be. In some cases I will pull out the text and make it larger. So if you're doing this on your laptop, you would check out your repo locally, go into that repo, and you can create a Singularity recipe. Any file in your repo that starts with the word Singularity, capital S, is going to be converted on Singularity Hub into a container. So it's going to be run on the Singularity Hub cluster to be built into a Singularity container. So you'll want to create, for instance, in this example, a Singularity Hello World example. And I'll just run through the pieces. So at the top of this recipe, you'll see this bootstrap and from text, and the bootstrap just tells Singularity where is it going to look for images to start with. So we're going to bootstrap this image from this container from a Docker image, and then the from tells you which image on Docker to start with. So in this case, we're going to use their CentOS. So if I was doing this on the command line, it would be Singularity build, the image file name, and then you would do the Docker ://CentOS. If you're familiar with the Docker Hub style of URLs, that's the way that would look. But in this case, we just say, okay, I'm going to take the CentOS image from Docker. And then the setup part of your script, of your recipe script, is run after the image is downloaded and unpacked on the local system. So either on Singularity Hub, or if you're running on your laptop, Singularity would download CentOS, unpack the file system locally, and then run the setup. And the setup, you can do things like copy codes into the containers, what will become the containers file system. It's an easy way to move codes in. In this case, I'm copying in this example hello world.cpp file in, and all you have to know is that the environment variable Singularity rootfs points at the base directory of the CentOS image file system. Okay, so this is run before you enter the container. And so then the post section of this recipe is run after you enter the container. So now you're in the container environment. You can run things like yum to do installations. You can compile your code. So in this case, that's what I do. I do a yum install of development tools so I can have GCC. And then I enter the directory where I copied my application, which I just created an area /my_app. And then I'm going to run GCC to build my application. In this case, it's a simple C++ hello world, which you would find in the GitHub if you go have a look. And then the run script part of this recipe, in Singularity, you can run your container like an application, and this just tells Singularity the application inside the container that should be executed in this case. And I'll show you how that actually, how the command actually looks like when you're running the, or no, see, I listed here, sorry, on the bottom of the bullets here on the left, Singularity run, and then you would type in the image file name. And when you execute a container this way, it runs whatever is specified by this run script in your recipe file. So there's also, you can also add an environment piece to your recipe. You don't have to. All of these pieces are optional. And environment really defines environment variables that will exist whenever you use the Singularity run command or the Singularity execute command. And so in this case, I'm just adding my application path to the path environment so that the application would be found by default, even though in my run script I specify the path explicitly. So once I do a git add and a git commit and a git push, the push will trigger Singularity Hub to search the GitHub repo for any updated recipes, and it will trigger a build of the recipe file. So here you can see an image of Singularity Hub. You can see my singularity.hello world file. And you can see the current status is waiting. And that means it's in the queue for the Singularity Hub cluster to build that recipe. And that will change to running over time. Usually it's fairly quick, within seconds. Sometimes you might get an error. Let's say your recipe build has an error. You might find an error here, and in that case, you can click on error, and it will show you the build log where you can debug if this is where you're relying on your building. But eventually, you get complete when you've gotten all the errors out of your recipe, It will go to completed, and at this point you can download it on Theta. So here's an example of doing that. So we log into Theta, we can run this Singularity build hello world.simg, and then we provide the URL to our image. So in this case, it's on Singularity Hub. It's in my user area. I have the GitHub repo name, and then my file was singularity.helloworld. So I'm going to do :hello world to tell it which Singularity recipe to grab out of that GitHub repo. If you just if you don't have that colon, it would by default look for just a recipe file with only the name Singularity. And if you don't have that in your file, if you don't have that, you would get an error. If I tried downloading from this repo without the hello world specified, it would throw an error and tell me that container doesn't exist. So you can see here where it essentially downloads, that's the progress bar, it downloads the image, and then builds the file hello world.simg in my local directory. So now I can run the container just with simply saying Singularity run and then the hello world.simg, and you can see it executes my hello world C++ example. Otherwise, you can also enter your container's environment if you want to inspect the container, for instance. You could do Singularity shell image file, and that's going to bring you into a shell that's running inside the environment of your container. Now on Singularity, whenever you do this, Singularity always mounts your home directory by default. So you'll find when you do this, you'd be in your home directory or wherever it is that you started up the shell. But you can see at the bottom, I can also ls into this my app area where you can see the .cpp file that I originally copied into the container. You can see I can echo the path, which I adjusted in the recipe to append this my app area so that the binary would be in the path. So you can see we're inside that environment. Another thing that's useful for sort of debugging and probing your container you might have is the exec command. So instead of entering a shell and executing commands, you can do Singularity exec with your image and run commands and then specify commands that you want run in the container environment. So this doesn't enter a shell, just it's a single one-off command. So here you can see me running echo, you can see running ls, and it shows me that my app area. Here's an example of running or of printing out an environment variable that's inside the container, which is a bit convoluted, as you can see. So just running echo path doesn't work. You need to run bash-c with the echo, and then you get the internally defined path variable. And that can be useful for, if you are having trouble with LD library paths, trying to, as we see, these LD library paths will become important for running MPI applications with Singularity. It's useful to be able to probe that internal environment while you're debugging. So let's move on to MPI-enabled applications. So here is a recipe. I include a link at the top right to the GitHub for this recipe, and actually I guess no one has the slides at the moment, but these slides will be posted when at the end of the talk. So let's see. The challenge of using the MPI-enabled containers, of course, on systems like Theta and Cooley, is we have custom MPI libraries that enable the use of the Cray high-speed interconnects that connect all of our nodes together. So just compiling MPI in your container isn't sufficient. You need those custom libraries that are provided by Cray and sit on our file systems. So I'll show you how to build MPI into your container in such a way that you can override the container's version of MPI with the local version of MPI. And this is an example of that. So here we, in this recipe, I have in the post section, so this is after the recipe is inside the container environment. We download a version of impitch in this case, and we untar it into a local /mpitch directory. And the trick here is that when you run the configure command, you need this disable wrapper rpath specified. This disables functionality in the MPI build wrappers. So, when you're building MPI, you use these MPI CC and MPI CXX to build your software instead of G++ or GCC. And if you don't include this in your configure, those commands, those build commands, will automatically add to any dynamic library a pointer to the local mpitch libraries that are in your container, which will make it impossible for you to override the container mpitch with an external version. So that's really the trick there, is just adding that to your configure, and then otherwise you just build mpitch. And I'm explaining that in this text. I tried to include all of the pertinent text so the slides are readable. So now the trick is running, so in this case, running the MPI application on Theta. You want to first swap out, so this is our qsub submission script. I'm going to assume that everybody's loosely familiar with submitting jobs on Theta. This is an example submission script. Again, these are all in the, they will be in the GitHub that I'm using for this example. So you can find the code there, which is what this link is pointing you at. So at the top, this is the Cobalt submission command line variables. So we're running for 30 minutes on a debug queue with 2 nodes in the data science project, which you guys would need your own project to run there. And the first thing I do is I swap out the standard Cray mpitch library with a version of the mpitch library that has this ABI application binary independent compatibility built into it. So that means this is explicitly to support cases where you have a version of code that you built against mpitch externally, and then you're bringing that binary to Theta, and you want to link against this version of MPI dynamically. So that's what we do there, and then we add the Cray libraries to our library path. We also need this additional library, which I won't talk about, but it's required for the MPI. And then in order to get the LD library path that we have now in this external environment into our Singularity environment, we export Singularity env underscore LD library path and set it to our current LD library path. So in the case of Singularity, let's see, did I zoom in on that? No, okay, so I'm going to go stepwise through here. Let me catch up on my slides. So whenever we want to pass an environment variable into our Singularity container in this way, so instead of in the recipe file where we had that environment section in our recipe file, if we want to dynamically add environment variables just before we run a container, we can use Singularity env underscore. So any variable that's prefixed with that in our environment will be added to the Singularity environment. So here, this is where we are setting that LD library path for the Singularity environment. And then finally, we submit we run our MPI job. We use AP run at Argonne at ALCF. So here we run AP run with the total number of ranks, some number of ranks per node, and then comes the Singularity run command, and we specify our container. But you'll notice here we also we use this /b option of Singularity, which allows us to mount external paths internally into the Singularity container so that those paths will be accessible. And all the Cray libraries are sitting in our /opt area. So I just what they call bind mount the /opt area to /opt inside the container, and I do that read only. Obviously, we can't do it read write because we don't have permission to write into that area. So then we have this recipe. We've built, we built it on Singularity Hub or on our local system, and we can extract it from Singularity Hub using Singularity build, which you see here in the top pane. And then we can submit our job to Theta using qsub and the contents of this submit script that's in the white window. And then we specify the Singularity container for the script. And you would see in this case, in the Singularity recipe, I had copied in an MPI enabled calculation of pi. So you can see here we're running on 8 ranks across 2 nodes, so 4 ranks per node, and calculating the value of pi using the container. So now let's move on to some more complex things. Let's say we want to bootstrap images based on previous, or let's say we're going to make something really complicated. So say you have a multi-step build process for your software that has different tools that you depend on. I would typically recommend having stepwise recipes where you start with your Docker CentOS, you do all your yum installs for requirements that you need, and then you create another recipe that takes the output from the previous and adds things to it. And this is mainly to save you time. So if you have stepwise recipes and you find that the first or the second step has a typo, or you have to debug it, if you put that whole recipe into a single, or all of those steps into a single monolithic recipe, you have to do all those steps every time you find a bug, and you have to go back and redo it. But if you do it in the stepwise way, where you have, you're building on previous recipes to do a consecutive adding of software, it makes it a little more manageable, and you don't waste quite as much time. So I'll go through that real quick. So here's, again, I have links to these recipes in my GitHub. What you see is my first image recipe up here on the top right, where I'm simply doing some yum installs. I'm installing DevToolset 6 because I want to have GCC 6 and CentOS defaults to GCC 4.8.5. And so I'm going to create an image that just has this DevToolset 6 so that I can have updated GCCs. So that's one recipe and will be one image on my Singularity Hub. So the next recipe on the bottom right pulls that image, that dev toolset 6 image, from my Singularity Hub area and adds Python 3.6. So now I have, so this derived image would have GCC 6. In this case, I think it's 6.3 is what comes with dev toolset 6. And then I would also have access to Python 3. And these are actually steps that I took out of, I added this Java. These are steps I took out of a build of TensorFlow, in fact. So these are requirements for TensorFlow if you're building that from scratch. Next,
Taylor, we
yes.
have a question on the chat.
Sure, go ahead.
It's what happens when the build environment includes terabytes of data files?
So, I mean, so you're going to bring those into the image, or you just require them to be accessible? If you're going to bring them into the image, I'm not quite sure what the performance impact is there.
So it sounds like, if I would say, I'll carry the question forward and say that I take it you probably would not recommend that for the obvious reasons that it's huge. So how would you cope with the need for data files that big?
So what I would do, if you need them during the build steps, obviously you're going to have, you're not going to be able to get those onto Singularity Hub, so you're going to have to build those images locally. And you'd have those input files on your local file system, and then during the build steps, you can mount those images into your build steps so that they're available, but they don't have to be part of the image. And then when you're actually running on Theta, you can have those images or those files somewhere on the file system on Theta, preferably the Lustre file system with some healthy striping, and you would, bind mount those again when you're doing your run or exec commands in Singularity. Does that make sense?
I think so.
So let's see. So now I am going to add mpitch to these images. So now I have this, I'm building, this is just a quick recipe. Hopefully it's legible, not too pixelated. So I build on top of this dev toolset 6 and the Python 3.6. First thing I do is I set up my dev toolset 6 so that I can use the GCC version. I'm going to build mpitch again with the special configure command so that I can overload it later. And I'm also going to do a pip install of MPI for Pi after I've done all of that, so that I have MPI for Pi available in my recipe. And I also have an example MPI Pi, an MPI enabled Python calculation of pi, similar to the C++ version, which I'm adding to the recipe as my run command using the Python 3.6. You'll find in that GitHub repo, I also have a recipe for mini conda installations. This is actually how I built, it's a recipe for building a mini conda installation with PyTorch, TensorFlow, and Keras included. And it's what I used to produce the one that we provide here at Theta for users, which I'll mention. And I mean, the main trick there is that in Miniconda, there is an Intel specific channel that you can enable, and then it will download the Intel optimized Python, the Intel optimized TensorFlow, and so on, so that you get those benefits on the Knight's Landing when you're doing your machine learning in TensorFlow or PyTorch. Keras is included in there as well. So let's talk a little bit about performance. Are there any questions about, building recipes? These recipe files, besides these, setup, post, environment commands, otherwise they read like bash scripts. So I don't see I guess I'd have to exit the presentation to see if there are questions. So okay. So let's talk a little bit about performance.
Taylor, there is a question.
Oh, go ahead.
Do build environments have such large data requirements to build the software environment? If so, I'd like to hear more about a requirement in more detail.
So you're talking about how much disk space you need to build?
Usually the large data requirements are when you're running the container, so you'd leave them on your shared file system and or home dir, which get bind mounted to your container and during Singular, as Taylor explained. So it's a comment, not a question.
Yeah, that's from Andrew. He would. Yeah. Okay, so talking about Singularity performance on Theta, file I/O on these machines is always an issue, and particularly in the case of things like TensorFlow, where you've got large numbers of Python imports. You're doing lots of small library loading. In high energy physics, we do this where we spread out our codes over many shared libraries. So any of these cases where you have dynamically loaded libraries, lots of them, lots of Python imports, lots of fstats on your file system, Singularity can actually improve your performance for metadata style activities. And so I did some quick tests using the mini conda recipe for TensorFlow, and I just ran the Keras MNIST example that comes out of the Keras examples area, and I just measured the import time inside and outside of a container. So the top plot, you see varying numbers of, in this case, just MPI ranks, all of them doing all of the importing that you see in the Keras MNIST example. And I ran it multiple times because we tend to see slightly different performance from run to run, just depending on file system occupancy. What other people on the system are doing can affect our performance. And you can see it does vary quite a bit. I also show the mean performance in dotted lines and the sigma in red at the bottom across the runs. And so, it's not a large sample, but you get a gist that if you have, in this case, Miniconda installed just on Lustre, and you do these TensorFlow imports across some number of ranks, the import time can vary quite a bit and seems to take off, at the 2,000 to 4,000 ranks, all doing it at the same time. You start to see the import time is growing linearly there. It's no longer, you're just losing performance there. So if you do this inside of Singularity, which is the bottom case, so this is now doing all of the imports inside a Singularity container, you can see, first of all, you get much more stable performance from run to run. but you also get much better performance as far as total load time. So, but you can also see that even going from the 4,000 to 8,000 nodes, or 4,000 to 8,000 ranks, the performance starts to take off. So even inside of Singularity, you start getting some performance problems above 4,000 ranks. But it's still, we're talking about under 30 seconds at 4,000 nodes. So this is something you should be aware of, something you should measure with your, everybody has their own, custom thing that they're doing. So just be aware that sometimes you can see performance benefits using Singularity. If your software is not necessarily, traditional HPC friendly types of software, which I would say, Python imports were never intended for large numbers of ranks all trying to do it at the same time. It's, traditionally people talk about doing static builds of binaries so that you avoid these kinds of scaling problems, but obviously you can't do that in Python, at least not without some additional libraries. So just to make this easier to see, I took a ratio of the bottom and the top, and you can see the import time performance in general is 2 to 3 times better inside a container versus just directly off of Lustre. And more generally, we actually had a summer student, Spencer Williams, over the last summer, who measured this explicitly. So he created a container with a few hundred files and literally just did a bunch of OS path exist calls, on the file. So really just metadata operations. And in general, he saw performance benefits a factor of 7 if those files are sitting in the container versus on Lustre. So you can, metadata performance is, much more or much better mitigated inside of the container versus outside. So let's see. So I mentioned also the Lustre striping. So if you've got big containers, the containers we've been talking about with, say, the DevTools and the Python 3.6, these containers are in the gigabyte range in size, so they're not too big. But we've definitely seen cases of containers reaching, hundreds of gigs. And you, of course, want to take advantage of the fact that Lustre does striping. And the default for our system is using a Lustre striping count of 4 or 5, I think it is, and I think the default stripe size is 8 megabytes. But if you've got these bigger containers and you're going to be running lots of, or if you're going to be running large scale jobs, so thousands of ranks, I would recommend setting that set stripe to something like 50. I think we have a total of 53 or 54 Lustre servers that can hand out these stripes, but the recommendation is always to do just a few under the max in case there are some number out for repair or whatnot, that you don't end up having trouble there. So in this case, you would create a directory. You would set this Lustre striping. I include the Lustre, the LFS command here. This is the command you would run on Theta on the login node, and then you would copy your file into those directories. So we have some pre-installed containers on Theta and Cooley for your enjoyment. I mentioned the Miniconda install. This has the TensorFlow, PyTorch, and Horovot. inside. There's also a container for the MPI file utils package, which can be useful if you're trying to do parallel copies to the SSDs, for instance. If you have some files you want staged on every node and you want to take advantage of the SSDs, there's something called an MPI CP inside that container, which will do a parallel copy from a single file on Lustre and put it on all the SSDs across the machine. On Cooley, we have a container for TensorFlow and a container for PyTorch. These have the NVIDIA backends installed so that you can take advantage of the Teslas that are there. And we have documentation for running Singularity on Theta, at this top URL. And then we have a special additional page for the Cooley implementations that you can see both there. There are also, in these directories, you'll find example submit scripts so that you can see how to use those. And that's pretty much it. We have Singularity on Theta and Cooley. I recommend these stepwise builds if you have a complicated build. Lots of steps in your building up of your software. Use these derived containers to isolate stepwise that workflow to make it a little more manageable and make debugging less time consuming. The building of custom containers has to be done off-site at the moment. There are some efforts, I think, to change that and make it a little more doable on the login nodes, or setting up essentially a local Argonne instance of Singularity Hub that would allow you to do builds that way. And I also covered a little bit of the performance benefits of file system metadata access. If you need help or have questions, of course, check the documentation so that we aren't having to repeat, but feel free to email data science, the data science team, and we will get back to you. So that's it.
Thank you, Taylor. Are there any questions? There were a few additional comments in the chat. Dave Dykstra commented that CVMFS also moves metadata operations to the client, so it should have a great improvement for the file I/O on HPC systems. But for some reason, HPC administrators mostly don't allow it and don't even offer to try it.
So Dave, I've actually had, Ryan, I know Dave from High Energy Physics. I have had many conversations with the operations crew here about CVMFS. One of the challenges is, of course, that it depends on Fuse, which means you have to install a Fuse module into the worker nodes of Theta. And they are a bit wary of the security, having to pass that through a security review. Because Fuse allows users to mount file systems. I don't understand the details of why there would be reservations there, because I don't think you would be able to mount anything that you wouldn't be able to already just copy directly onto Lustre or such. But in any case.
Singularity is a bigger risk than CVMFS. Set UID root. So.
Well, in principle, that's why we're running Singularity, right? Is because you can't. Singularity won't. If Singularity runs the container using the user's.
Right.
the user ID, essentially.
right, but it is a setuid root program. So it is taking that risk, and CVMFS doesn't require root, although it does require, you could restrict Fuse to only allow the CVMFS user ID to use it so that ordinary users can't. So when it's installed by the system administrator, it's less of a risk than Singularity.
Well, why don't let's take this offline.
Sure.
Because, I mean, I don't understand all the details of it, and
Sure.
I think, it could be useful to have more conversation.
Having both Singularity and CVMFS on the HPC systems would be wonderful for high energy physics.
Right. So let's see. I see someone saying, can Singularity be built anywhere and run anywhere? I don't see why not. I know Andrew is online. I'm not exactly. I am pretty sure Singularity is open source, right? Or is it?
It's open source.
Yeah. So there you go. So it's open source, so it should be able to be built and run. The question is whether or not it supports non-traditional x86 architectures. I don't know.
It does.
It does. Okay. So there you go.
If we're on the topic of loading things fast, I'll just mention that there's a tool called Spindle from Livermore that lets you load things fast without having a container. It's transparent and it uses LD.SO to do that. We use it in production,
Okay.
but so it's another alternative to CVFS or CVMFS or Singularity, and it doesn't require you to do containers. But containers are awesome. So.
Let's see. Someone's asking the version of Singularity. I think at the moment we have let's see, am I logged in? Not logged in. I think we have 2.5 installed.
Better move to 2.6.1 because that's the only secure version.
It is 2.61 on Cooley. Just FYI.
Okay, then it's probably the same on both, is my guess, because the person that installs them, there's only one person that does it, so I would imagine that if that's up to date, then both. Let's see, what other are there here? So Andrew says, are some HPC apps or workflows that should specifically not try to use containers due to some limitation or issue? Not that I'm aware of. Can you explain why Singularity containers must be built off-site? So that is mainly because Singularity requires, if you're doing a custom build, so if you're going to run a recipe file, for instance, right? So you could run your recipe file on your local machine, but you have to run it with sudo. I don't understand the details of why that's required because let's see, and Dave says Singularity 3 supports building images without sudo, so hopefully we can move to Singularity 3 at some point. But so that was always the restriction, is that you needed sudo access to build custom images. And so we do not want to give users sudo access on the login nodes. So that was the restriction. Let's see. Import a Docker image or build a basic container without needing root. That's correct. Todd says you typically need sudo because you want to call the system package manager within the container. Any other questions? any special considerations for IB support within a container? That acronym needs to be expanded for me. IB support?
InfiniBand.
Oh, InfiniBand. So like I said, with in order to get that InfiniBand support, you need to link against the local proprietary libraries, right? I mean, the Cray impitch library is proprietary. We don't have source code for that, so you can't build it into your container. If you I would assume that, if you just have your own system and it's sort of out of the box InfiniBand, that you should be able to copy those libraries into your container if you wanted to. And I'm sure you could do the same thing on Theta in principle, that you could copy the lib MPI.so into your container, and instead of having to do the linking externally. And yes, there is a Singularity users group. Dave points that out. They're going to have their meeting soon.
So Greg asked, what is your advice for installing and using Singularity for the first time on an HPC system?
You're asking the wrong person. I was not involved in installation of Singularity.
Okay.
I don't know if Alex is on. I think he handles all of our local installation.
There's a request about the recording of this. We are working on getting the entire series up. I'm not quite sure, but we will send out an email to the attendees when we have something.
And where will the slides be available?
Actually,
I'll probably
send out a link. We'll send out a link. It will come through Eventbrite from your registration to all of the people who registered.
And I'll probably link to my slides on our Singularity page. So if you search ALCF Singularity, in the next day or so, those should appear there as well.